Okay. Um, this is the third time I've tried to click start stream. Um, okay, and it's finally working. Okay, nice, nice. Yeah, okay, for some reason, whenever I click start stream on YouTube, sometimes my encoder, maybe it's OBS glitching, maybe it's on YouTube's end. I don't know whose fault it is. But yeah, it just, I'll click go live and then it just won't work. But today, so we've been doing Commodore 64 manual streams, right? I've just been going through the manual, but I'd like to try today doing some Leetcode problems. So I think that'll be fun. I don't know what I'm getting myself into. I don't know how, or I know, I think we have a little bit more of the manual to get through, and then I want to do some Leetcode problems. But like, I think we need to do a couple things like a 2D arrays. Look, I need to brush up on how to do basic arrays some more. So yeah, I'll leave the stream title as is. So let's go back to the main scene and let me listen real quick. As is. So let's go back to the main scene and let me listen real quick. Okay, sounds fine. Beautiful. Well, yeah. 10 print. Welcome. Welcome to Code Orangutan. 20 go to 10 run. Yeah, so planning on just continuing through the Commodore 64 manual until we get to what's it called? And oh gosh, I gotta restart my freaking, you know what? No, I'm not doing it. I just need to fix this like program or whatever. Okay. So you can see like on like the edge of my screen, I have all this stuff open. I have like all this like command line output printed because I have this like Python script that lets me use my Ableton Mini Launchpad as like a stream controller thing. And it works, but there's one feature that I was trying to add, which is where if I press a button, it'll add a timestamp to a file. So if I want to make a clip, I can just go through the timestamp. I can just go through the file. It'll make it way easier to find what I wanted to clip. But it is not working for some reason. I need to do some troubleshooting with it. But you know, whatever. I'll do that. I'll have to do that like off stream because obviously I can't do it on stream. But yeah, so I wanted to Zathura home downloads Commodore 64 manual and put it in the background. Okay, so we'll have to switch around, do a little dance with our OBS scene here, and bam, here we have our manual. So we're doing arrays on the Commodore 64. So let's do it. New. Start a new program. If you tried to enter more than 10 numbers in the previous example, you got a dimension error. Arrays of up to 11 elements may be used where needed. Just as simple variables can be used anywhere within a program. Arrays of more than 11 elements need to be declared in a dimension statement. Okay. Why on earth is it 11 elements that you can just freely use, whereas you have to declare larger ones? That's the weirdest. That might be the strangest, like, strangest, like, programming. You also have the stopwatch. And wait, okay, the stopwatch is going. Here, let me edit properties. I'll bring it onto view. Last time it said 2 hours 58, so it's gonna be what? It's gonna be 10, and it's gonna be 8 here. Okay, that's how long we've been speedrunning the Commodore 64 manual. But wow, what a strange, really, truly, what an odd feature of a language. Like I look at here, let's look into that to explain. Here, let me go to BRB real quick because I had, let's see, why is 11 items the limit of an array in basic Commodore 64? Okay. C64 wiki. All right, let's check out scene 2 here. So, and this is going to be a good reference, I think, for me. An array is a group of variables that all share the same name. The specific variable in the array is referenced by using its array index. Array variables can be of the type integer, float, or string. Okay, that's all good. Examples of array variables. As can be seen, an array can have 2 or more index variables. In C64 BASIC, arrays can have as many as 255 dimensions altogether. The total number of elements in an array is found by multiplying the maximum index numbers of each dimension together. If an array is to contain more than 11 variables, also known as elements, or to be multidimensional, then a dim statement it must be set-aside memory. But why is 11 the default? I'm wondering if there was some like heuristic they ran. And you know what? Hold on a second. Let me put this thing on my mic. I wonder if there's there was some heuristic that they ran that made it I don't know. I really don't know why. I have no clue. I have no clue why that's the case. Anyways. Okay, this lets the computer know that you will have a maximum of 100 elements in the array. So I can say, okay, so line 10, I can say x, goodness, what is it? Man, I'm forgetting all of my hotkeys. I can say this equals 13, and I can say 20 dim b with x. Run. Okay, so it partitioned an array, not partitioned, but allocated an array of 13 elements. Okay, this would dimension the array with the exact number of values that will be entered. Be careful though, once dimensioned, an array cannot be redimensioned in another part of the program. Interesting. You can, however, have multiple arrays within the program and dimension them all on the same line like this. Okay, so you cannot redimension. So I wonder if there's a way to do dynamic arrays, or if perhaps there is a way to do pointers in BASIC. I don't know. As programs become more complex, using subscripted variables will cut down on the number of statements needed and make the program simpler to write. A single subscripted variable can be used, for example, to keep track of the number of times a particular face turns up. Okay, so yeah, let's write this program. Rem dice simulation print $$ $147. That's 146. 10 input. How many rolls? And we'll say that we want this into a variable that contains numbers called x, for L equals 1 to x. 30, we'll make a random number. R equals int, and we're going to do it from the range. It looks like 1 to 6. So it's going to be 6, the maximum, times R&D 1. And then we'll bring it from 0 to 5, and 2, 1 to 6, with adding 1 at the end there. 40 F R. Okay, so faces at R equals faces at at R plus 1. So okay, F contains the face count, and we don't have to pre-dimension the array because we know that we're only going to be generating numbers between the range of 1 and 6 inclusive. So we wouldn't need a dimension statement. But suppose we want to do a D20, then we'd have to pre-dim the array. So 50, next L. So we'll go on to the next roll. I don't know why it's called L. 60 print face, comma, oops, in order to do a nice little tabular display here, number of times. Okay, 970 for C equals 1, 2, 6, print C, F, subscript at C, next. Okay, so yeah, this is a pretty simple program. Let's just run it. How many rolls? Give me 10. Boom. We had one roll that was 1, 2 rolls that were 2, 3 rolls that were. We rolled 2 rolls that were 0 rolls that were 3, 2 rolls that were 4, 1 roll that was 5, and 4 rolls that were 6. Man, I was lucky. I was lucky, I guess. Okay. So let's run that again. I wonder how high we can go. Let's try 10,000. It's taking a while to crunch. Man, this is a program that would take like a second on a modern computer. Oh gosh. Oh, I hope it's okay. I don't think we'll run into any particular memory limitations because I know that 10,000 is going to be below the maximum range of a Commodore 664, a C64 integer. And I know that yeah, our array is only in the range 1 to 6. Yeah, it's just going to be slow. So, all right, I'll let this program run it. I'm realizing I haven't showed you a single thing on screen. That's my bad. Anyways. Well, yeah, let's just wait and I'll. Okay, so just as a comparison, the following is one way of rewriting the same program, but without using subscripted variables. Don't bother to type it in, but do notice the additional statements necessary. So here's the no subscripts version, and it is definitely much longer. You have all this conditional logic, all this yada yada. The program has doubled in size from 8 to 16 lines. In larger programs, the space savings from using subscripted values will be even more dramatic. Cool. Two-dimensional arrays. Earlier in this chapter, you experimented with one-dimensional arrays. This type of array was visualized as a group of consecutive boxes within memory, each holding an element of the array. What would you expect a two-dimensional array to look like? First, a two-dimensional array would be written like this. A4, 6. Those are the subscripts, and can be represented as a two-dimensional grid within memory. The subscripts could be thought of as representing the row and column within the table where the particular element of the array is stored. Okay, now I'm wondering, our program is still running. I wonder, here, I can open up our little video menu here, and I wonder if there's a way I can can I hardware accelerate this? Okay, enable drive, we don't want any drives. Parallel port enabled. GRAM disabled, RU, RAM expansion unit disabled. Real-time clock, auto. Yep. Reset and run. Save autoplay, boot easy flash, system ROM, C64. Loadable, yeah, I think we're on, I guess we're on Dolphin DOS. Turbo mode on. Yeah, how turbo can we get? 4? Oh man. Here, let's escape and just run. And let's say 100. Okay. So let's turn off turbo mode. How fast did it actually become? Turbo mode. Why is it? Turbo mode, yeah, turbo mode's smart, I guess. We'll off for now. Okay, and then let's run it with 100 rolls. Okay, and that felt like about the same time. Here, wait, let's run it with 1,000 and see how that feels. Because 1,000 was the example in the book, and surely it wouldn't take that long if it was in the book. But we have already found one mistake in the Commodore C64 manual with the undeclared variable in, goodness, one of the audio examples. had an undeclared variable, or rather it used a variable that was completely undeclared. I also want to note one thing, is that arrays seem to be 0 initialized. Like if we go back up here, line 30 of our program, okay, yeah, so it finished. So let's turn on turbo mode, smart, 4x, run 1000. And we'll see. Okay, that definitely was faster, but I think we'll turn it off because I want the real authentic experience. So if we list our program on line, what is it? Line 40. You'll see that I did f subscript r, so like the array faces at the rth index, the random face index, equals f at r plus 1. So this is assuming that all of the elements in the array initialized to 0, which is not an assumption that you can usually make, but I suppose it is an assumption that we can make in BASIC. That might have been taught in the manual earlier, but I don't recall seeing it. Okay, 2D arrays, yeah, they make like a table. So yeah, I can say like dim a with like, give me 5 by 5. And I could say a at 3 by 2 equals 1. And then I can say print a 3, 2, and I print 1. And oh yeah, I guess that's a way we can check. Print a at 2, 2. And it should be 0. Yeah, okay. If two-dimensional arrays work like their smaller counterparts, what additional capabilities will the expanded arrays handle? Try this. Can you think of a way using a two-dimensional array to tabulate the results of a questionnaire for your club that involved 4 questions and had up to 3 responses for each question? The problem could be represented like this. Are you in favor of resolution 1? Yes, no, undecided, and so on. Yep. The program to do the actual tabulation for the questionnaire might look like that shown on the page 103. Okay, so yikes. I'm not typing all this in, but this is definitely like feasible. We start off with 4 and we print the answers. We get the input. And then, oh, I guess you can automatically dim with dim to below 11 with multi-dimensional arrays too. Interesting. Okay, appendices. Okay, so yeah, we're done with the Commodore 64 manual. Wow. Okay. So I guess Commodore 64 manual, we can stop the timer there. You know, go post that on speedrun.com, I guess. That'd be pretty cool. And let's add what? 24? 24? Enter. Yeah, cool. Reset. Yeah, what do we want to do next? I said we want to do some Leetcode in Commodore 64 Basic. So let's edit the title of the stream. Oh yeah. Doing Leetcode on the Commodore 64. Doing Leetcode. And save. Okay. Yeah, I guess we low-key don't need a manual anymore because I think I'm probably just gonna switch to the wiki if I'm being honest. And let's switch you to 1, you to 2, you back to 1. I need to learn the hotkey to like swap positions of windows because like here. This is what the stream looks like. In order for, like, if I go to this main scene, you see how this browser is being displayed? No, here, I was listening to King Crimson earlier. But Do you see how this browser is being displayed? It has to be on the left side of the screen specifically, because like this display, it's actually just my whole computer, but just kind of like pushed over to the side. But yeah, anyways, let's go. Okay, list of Leetcode problems to solve. Let's see if someone's like, because someone definitely has curated like the list of good Leetcode problems. Neatcode's list didn't work. Okay, let's go to Neatcode. What's Neatcode? Okay, Neatcode 150, blind 75. Okay, I don't know if I'll do all 75 problems, but you know, we certainly can try. Here, wait, is this 75 total? Wait, 8 here. You know what? Wait, let's use the Commodore 64 to do this calculation. So okay, so 10 input, enter your number, quote, on into the value x, and then 20 if x is equal to, can I just do, is it, oh gosh, is it 1 equal sign? Is if x is equal to -1, then go to 10, then go to, or rather, if x is not equal to -1, then 10. So we're gonna just keep inputting numbers. Oh wait, no. We need a line 15 and say accumulated value equals a, what is it, plus x. Okay, and then we can say line 30, print total semicolon a. Go to 10. Syntax error in 10. Oh no, I forget. I already forget how to input numbers. Oh my gosh. Okay. C64 wiki input. Okay. Okay, it's a semicolon. Okay, so list. And the program's all kinds of messed up. Go to 10 now. So let's say I do 3. Or wait, let's just run it on this. Or let's do 1, 1, -1. Oh god, it didn't work. Okay, you know what? Yeah, we don't want line 40, 50, 60, or 70. Okay, so that's our program. Oh yeah, and then on line like 25, because we already added -1 to a, we subtracted 1, we need to go back and say a equals a plus 1. Okay, now run. So okay, let's do 8, 3, 4, 1, 2, 6, 11, 1, 2, 3, 6, 1, 10, 2, 2, 5, 3, done. That's 70. Oh, I missed the last one. There was a bit manipulation. Yeah, so this is 75. So this list that I'm sort of hovering over on screen. on the right side of the screen. And actually here, we can change this. We low-key don't need this timer element anymore. So we can here, low-key, let me do some scene organization real quick. You know, let's just show you guys my screen. Let's organize my OBS broadcast, shall we? That'll be fun. Edit you. Rename section header, section header. I'll just resize it as I need it. You are going to be named, and low-key, we can remove you. No. Cancel. Rename to small timer accumulated. And we don't need you anymore, so we can hide you. And you are rename to timer display. Okay. So there we go. That's all we want to do for now. And then I want to say Commodore 64 Leetcode. Boom. Make it big. All right. Back to scene 1. Or no, oh wait. Here, I'll have to move you back to over here. Okay, now we're doing Leetcodes. All right, I guess we'll start at question 1. Given an array nums, return true if any value appears more than once in the array, otherwise return false. Okay. So, all right, so there's like, okay, so here's one thing I'm going to struggle with when doing these Leetcodes, is that like, I know how to solve a lot of these. Like I didn't have to grind Leetcodes to get my job. Full disclosure, I didn't have to grind Leetcodes, but you know, like I did there was a time in my life where I was grinding Leetcodes to try to get software engineering jobs. You know, they definitely help you like learn algorithms. And does Leetcode have like basic? No, that's because it's a horrible platform that doesn't have real programming languages used on real computers. But no, so it contains duplicate. So if any value appears more than once in the array, otherwise return false. Okay. So one way I might do this is like the like naive way to do this is to go through every element in the list, right? Like we'd go through every element in the list twice. So I'd be on item 1, and then I'd look through the rest of the list and say, is there a duplicate version of this? No. Okay, move to item 2. Look through the rest of the array. Is there a duplicate version of this? No. Move to item 3. Is there a duplicate version of this? No. Move to item 4. Is there a duplicate version of this? No. Move to item 5. Okay, and I wonder, here, can I do like dim? Give me the dim manual. Okay. I want to see, how do I get the array, like the size of an array? How to get size of array, C64 basic. So I'm just going to assume that, you know, that it works. Okay, it does not have a built-in function. Len. Okay. Hmm. Okay, so I guess I'll have to pre-supply the array size. That's kind of funny. I wonder, yeah, whatever. Let's just try to write this program. So let's suppose we have an array n, and we'll say s equals, and the size of this will be, let's say we want, let's start off with these 4. Or no, okay, so give me a new program, and what is it? Bang, bang, bang. Okay, there we go. So on line 10, let's do s equals, and it's a real shame that I can't, just plug this into Leetcode and give it my solution and say, hey, run it with the test cases. But you know what? That's so well. Okay. Anyways, and then I want to say n, which is going to be nums, or ns. Nums is dim. Oh gosh, I forgot how to use dim. Dim ns. Yep. And I want 4 variables here. Dim ns with 4 variables. Is that right? Yep, that's right. Okay, so now what we want to do is, and that'll dim where I should be able to say ns at, here we go, 210. Can I say ns at 5? Subscript error, ns at 4. Syntax error. Okay, perfect. So we know it's working. So let's list our program. So now we want on line 20 for I equals 0 to s, because that's going to be the highest index. 30. Now for j, or actually no, it should be 2s minus 1. Because if we get to the last element of the array, then there's no more elements of the array to check. Do you know what I mean? Anyways, for j equals I plus 1 to s. Yeah, I guess to the very end. Okay, 40. If numbers at if ns at if ns at I equals is equal to, that's not the right one, is equal to ns at j, then I want you to go to line, let's go to line 60 for now. And then on line 50, we want, we want to next I, or next j, next j, 51, next I. So we want to go through our whole for loops, and if it's equal, then on line 60, I want to print just false. And then what is it? Ret? Does ret return? Good lord. This is what it's like learning a new programming language, guys. Especially one that doesn't have BRK. Does that break out of our program? Yeah. It makes a breakpoint, but is it return? Oh, is it exit? Ooh, do I have an exit command? Exit. Yeah, okay, I have exit. Or actually, what does Leetcode want the result to be? If it has a duplicate, then yeah, false. Otherwise, but if it makes it all the way through the loop, then we want to print true exit. Okay, so this is our program. So we first declare our array of numbers, then we're going to iterate element by element. And you know what? Here, let's do a quick explain scene. I need you to be on a new tab, and I need you to be on desktop 2, because when I go to scene 2, here we are. And let me not flashbang you guys. I'm sorry. Here. Okay, so we have a list of numbers here where it'll be like 1, 2, 3, 4, and let's change it up. 1, 3, 1, 4, 60, 20, 100, 2, 3, 2, 4. Sure. This one will have a duplicate. So okay, so here's how this program will work. So we'll have two variables. One's going to be called I, and this is just by convention. And let's make you pink, and copy paste, and then we'll have J. Okay, so let's look at our program. So we start off, and you know what? Let's just make it abundantly clear. Bim bum bum list. Okay, so this is our program. So we start off initializing our array to size 4, and then we go through. We have these two for loops: for I equals 0 to s minus 1, and then for j equals I plus 1 to s. So what's that going to do? So for I starts off at 0, because remember the array indices go from 0 to wherever. So 0, 1, 2, 3, 4, 5, and 6. Okay, so remember those are the array indices. So we start off I at 0, and then we start off j at next greater than I. Okay, so 0 and then 1. So at the beginning of the loops, it's going to look like this. Okay, and then it's and do I need to go? Sorry, I just looked over my screen and I realized I'm not in big screen. So yeah, so here's how it's going to look like. We start off with I at 0, index 0, and j at index 1. Okay, then we're going to take j and increment it inside the I for loop, right? So you can see line 30, 40, and 50 here are sort of the j for loop. So I is the same way, and then we check it against the element at j. And also, I'm realizing I got these flipped. So we want you to say FALS shift backspace E. And I want you to say true backspace, enter, enter, list. Okay, so anyways, yeah, so inside the for loop, I stays the same. Just sorry, I'm just checking to make sure that, yeah, I stays the same, and then j is going to be incremented and go up across the inside of the for loop. And then when j gets to the end, I increments, and then j gets reset to be I plus 1. So I is 1, now it's 2. And then it's going to go through the array element 3, element 4, element 5, element 6. It'll compare these and say, oh, element 1 and 6 are equal. Okay, break, go to line 60. So that's what if ns at I equals ns at j, then 60. So it'll go to line 60 and it'll say, yep, it's true. There are duplicate numbers here. We're done. So remember, basic arrays initialize to 0. So if I just run this program as is, it'll say true. Print true. Why do I have a syntax error on line 60? Is it semicolon is statement on the line? Yeah. Oh, I guess that's the exit code. No, wait, list. I want multiple statements on one line. Do I have to like exit 0? Exit 0. Oh, God, not exit H, exit 0. Run. Oh gosh. Exit. Oops. Exit in basic. Do loop for next. Okay, yeah, wait. So I guess it's list of all basic keywords. How do I end a program? Is it stop? The basic program can resume from there. Oh, is it end? Does that end a program? Okay, yeah. Okay, so here's what we can do. List. Man, I'm so foolish. End. Change that to end. And change that to end. Okay. Yeah, so now the program just prints true and then says ready. So what if we change our program and we say on line 15, I want ns at 0 to equal, and let's look at our Leetcode example. It's on the side here. You might not be able to read that well, but it starts off nums where the first element is 1. The second element is 2. The third element is 3. And the fourth element, and that's it, 3 is equal to 3 as well. So if we list our program now, we can see that we've initialized our array with some elements. So if we run, this should print true. Beautiful. Now what if we change it to where it will be false? So we go to the array, we go over here, and instead of being 1, 2, 3, 3, we make the array, equal 1, 2, 3, 4. And this is false. Bam. Okay. Leetcode done. We did a Leetcode problem in Leetcode. And just real quick, I want to look at the recommended time and space complexity. With O n time, yep, and n space, where it's the size of the input array. Yep, okay. So we did the brute force way. And yes, okay, it wants us to use a hash map. And by the way, I'm not convinced that the technical theoretical complexity of using a hash table is constant, but you know what, man, whatever. Yeah, wait, I thought hash tables were like n or like log n best. Wait, is hash table access actually constant? I don't think it is. Yeah, okay, yeah, okay, yeah, yeah. So it's technically false, but it's true enough in practice. So you know what, Neatcode, I'll allow it. I'll allow it. And okay, so Basic doesn't have a hash table. So how do we do a hash table in Basic? Okay. You know what, Loki, that would be interesting. That would be interesting. How do I implement a hash table in Basic? What are some basic basic? What are some basic hash table implementations? Let's start there. Simplest hash table implementation. How to write a hash table in C by Ben Hoyt. Okay. Linear and binary search, and then design and implement a hash table. Okay. So the simplest option is to use linear search to scan through an array. This is actually not a bad strategy if you only got a few items. In my simple comparison, using strings, it's faster than a hash table look up to about 7 items. And that's because of how this is because of what's it called, caching locality. I don't want to explain that right now, but it's because of the cache that you can do a small item array linear search faster than doing a hash table lookup. Okay, back in the yellow. Sorry, I noticed my mic peaked up to the red for a second. We don't want that. Anyways, simplest option is to use linear search to scan through the array. Cool. Make a struct. Can you do objects in Basic? I doubt Basic has objects. Does Basic have objects? So we'll have to. I don't think they do. Commodore 64. I really don't think it does, but you know what? That's fine. We don't really need like objects per se, but I'm thinking about how to represent like this struct here in Basic. You know what? Whatever. Each element is a string, key, and integer value. Okay. Binary search. A number simple approach is to put the items in an array which is sorted by key and use binary search to reduce the number of comparison. This is kind of how we might look something up in a paper dictionary. C even has a B search function in its standard library. Binary search is reasonably fast even for hundreds of items, though not as fast as a hash table, because you're only comparing an average of log numkeys items. Yep, that makes sense. Okay, so I understand what we're doing here. But I want to use like a proper like hash function. Random looking number. Hash modulo the number of elements in the array. Yep. That makes sense. What if 2 keys hash to the same value? We get a collision. You need a linked list to store the values that hash to the same index. Relatively slow is linear probing. Okay, yeah, I understand linear probing. Let's low-key do that. We try index 7 first, that's holding foo, move to index 8, holding baz, we move to index 9, and it's empty, so we insert it there. Okay. That sounds good. Let's think about how we might do this. How do you do, man, the Basic manual didn't implement. Does Basic even have functions? I know okay, wait, so it has this go sub command. Get hash. Oh my god, does it have hash tables? No, this is using devices. So let's look at go sub here. The I'm guessing we use this with def. Okay, so jumps to a subroutine at the indicated line number. This call is placed onto the stack. The subroutine finalizes using a return command. Program execution continues at the command following the initial go sub command. Many subroutines can be called consecutively, but the last one called will be the first to finish. When too many subroutines are called at once, the error out of memory in line whatever is thrown. When the number doesn't exist in the go sub command, the error undeft statement in error whatever happens. Okay. Yeah, how do I do a subroutine? Def defines a function with exactly one single numeric argument which can be executed with function afterwards. The definition may contain any legitimate mathematical expression consisting of mathematical and logical operands, functions, and variables, which finally results in a numeric value. Okay, so cool. So I think this is how we'll write our hash function. Okay, and the def has to fit into a single line. Okay. This can work. We can make this work. So we want a hash table implementation. So he starts up by defining the structure, allocating the hash table, destroying the hash table, getting an item from the hash table. Yeah. Okay. Basic subroutines. All right. Basic programming, subroutines and functions. Okay, we have a beautiful wiki book here. Function parameters. Okay, declare function. Okay. Commodore 64 basic multi-variable functions. How do I do that? Okay, so go sub 100. Okay, so I think we have to I think we're basically, what's it called? Wow, I think we pretty much have to think of this as though we're using like registers, and like we'll define a variable. I'll like basically think I'll kind of like declare the function and then use the variables within the function and then just hope for the best that they're never used again. So let's make a new program. Okay, so we're gonna define one remark hash tables dicts in basic in C64 basic. Let's see if we can implement this. And actually, okay, so I've been streaming for like about an hour. I know it doesn't say that I'm streaming for an hour, but you know, there were technical difficulties. I'm gonna grab a coffee real quick. So BRB. Okay, I'm back. So, all right, we have a little under an hour. Let's implement a hash table in Commodore 64 Basic. So let's go to the explainer scene. So let's talk about hash tables for a second. So right, this is actually going to be a great place to start. So here's how just like a normal, I say normal. Here's how like your standard array works, right? So suppose we have a statement that says, and here, let me grab these guys and move it down for a second. So ignore this for a second. Just ignore that. So let's say we're writing a program and we say, we say dim a, and we want an array of size 5. Okay. Or like the maximum element is 5. So what this does is in memory, so here we have memory is every piece of memory has a particular address. Okay. So each of these cells is like an address in memory. It's like a cell of memory. Okay. So what basic does, and actually I don't know how basic works on the internals, but here every other programming language, what it does, well, it says A starts here. Okay. This is A. All right. And it might have some other metadata down here where it says like the length, or it says like the length is like 6 elements here. So this is how it'll define A in memory. And then, you know, of course, memory keeps going on. And if I have another variable here, I can say it'll say like this is where B is. So let's just say I have a variable B, and its value is 5. So B equals 5. Okay, so that's the memory layout for this program here. So B equals 5, dim A 5, or low key swap these. We have a basic program. This is what the memory looks like. Okay, so arrays are great. We can store things in our array. So here's an example of an array, right? The blue numbers here are the indices, and the big numbers are the values stored in them. Okay, but what happens if we want more than 6 indices? So essentially, and let me take another drink. I apologize. So if we want more than 6 indices, well, like let's say our data set goes from like, 0 to 3 and then 100 to 105. Okay, so our data is indexed like, it's going to be like 0 to 3 and then 100 to 105. Okay, so the total possible indices that we want are 0, 1, 2, 3, 100, 101, 102, 103, 104, 105. Okay, so how do we work with these indices in a hash table? So one way we could do it is we could just declare a huge array, right? So let me grab my little memory thing here. Control copy, paste, move it down here. So we could just declare a massive array. And let me copy all these guys. Come on, there we go. All right, so we could just make the array bigger, and even say like in here, it'll be like ... Sorry about my clumsiness here. Where we have indices, 0, we want it in blue, 0, 1, 2, 3, a bunch of spaces, dot, dot, dot. And then we have like, 103, 104, 105 down here. Okay, so this would work if we wanted to assign values to this range, right? Obviously that would work. This would just, poof. It would all go together. But you see this big area in the middle full of all these empty values that we knew beforehand are going to be empty? We do not like this. We want to be efficient in our memory usage. We want to use as little memory, as we have to. Sorry, I was checking my mic was on. Yeah, so we want to use as little memory as we have to. So what we'll have to do is we're going to map these numbers. Okay, Control copy, Control V. Oops, no, don't paste a chart. Control copy, Control V. So we want some way to take these numbers. All right. These numbers. So this is going to be called our keys. Or low key. Here, wait. Keys. And we want to be able to map them. We want some function. We want it in white. We want to have a function that can take a key and output an array index in the right size range. Okay. So, right, take this array, it has 6 elements, okay? With these numbers, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so we want to map all of these values to a unique number within the range 1 to 10 in the right size range. And in our example, 1 to 10. Okay. So then once we have that, then we can have an array just like before. Let's take this and here, delete that. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's take our box. Is this 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect. Okay, so we can get rid of these. So under the hood, it's going to be mapped to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so these are the indices we actually want. But we can start to think about these numbers in a different way. We can say instead of 0 through 9, what if instead we had our function up there and it was a function of 0 and it was a function of 1. It was the function of 2, function of 3, and then here's the cool part, function of 100, right? That would map to each of these values. So let me make the correspondence clearer in my little illustration here. Me an arrow. Bam, 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 bam. Then so let's say this array is called A here. We'll say A. Right. So we would access these elements by going, we want A at element 0, but in our case, we want a at the function of element 0. Okay, so 0 is our key, and then we'll want to be able to do this up through our 105 key here, right? All right, so what we've done here is we've described a dictionary, right? This is a dict in Python, in JavaScript. This is a hash table. Let me explain why. So this function here, what I've described, is actually something called a hash function. Okay, and this is the hardest part about, well, it's not, but well, maybe. Yeah, this is one of the more difficult parts designing a hash table is finding a good hash function. And in fact, there are ways to do hash functions where, like, okay, so like a standard a language comes with, most modern languages, if not all modern languages, come with a hash table in their standard library, where you can just use the hash table as a dict, oftentimes with arbitrary keys and arbitrary values, right? You don't need to type any of this. Sometimes you do, but whatever. That's not a big deal. Very often, these hash tables are going to be good enough. They're fast enough. But if you're in a really high performance application, one kind of like maxim to keep in mind when you're doing programming is that the more specific information you have about your inputs, the better speed and output you can do, right? So the more knowledge you have about what's coming in, the better you'll be able to process it. So if you know some information about your hash tables, right? So if I know that my hash table is going to be just these keys, potentially, then I can write a really simple hash function. Like I might not want to use the built-in standard library hash table. I might want to use my own, where basically we just map a function that says if the key is less than 3, then just return the key. Otherwise, return the key minus what would that be? Minus 96, right? And let's write this as a basic hash function. So for our example, we can say example hash function. We'll say let's do Python syntax. Example hash function, and we want to input the k for key. And let's just do Python syntax. If k is less than or equal to 3, then we want to return k. Else, return k minus 96, right? And this is going to be a function that maps. It'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. And this will be a very fast hash function. So this is going to be a workable hash function for our particular data. But let's go back to what we've been working on. Okay. We've been working on blind 75 duplicate nums. We don't know how big the nums are. I wish there was a way, man, I wish I had like a unified, Commodore 64, like Leetcode, Neatcode, whatever, testing platform. That'd be awesome. Whatever though. Let's think about some example hash functions. So yeah, suppose we want to take any value. Suppose the keys are just these integers, right? We have this basic hash function here. There's also a universal way to essentially clamp the number, any number, into a specified range. So this is called the modulo function. So it'll be modulo hash function. All right, and the modulo operator is defined with the the parenthesis sign. So it'll just be k mod 10. Return k mod 10. And the way modulo works is like you can imagine a circle. Okay, so we have our circle. And let's use mod like 2, 3, 4, 5, 6. Yeah, I'm lazy. We'll do mod 6. Okay. So normally, right, if we have numbers, you can think about them on a number line. 0, 1, 2, 3, 4, 5, 6, 7. Okay. But when we're doing modular arithmetic, we'll start off, of course, counting at 0. And then we'll go to element 1, element 2, element 3, element 4, and then element 5. Okay, so this is what mod 6 would get us, where we can do an example. Let's say we're doing mod, I don't know, mod 5 or mod 7. Okay, so 0, 1, or 1, 2, 3, 4, 5, 6, and then instead of going all the way around, we'll go to 7. Going like up to 7, right? It's not a number line, so we're wrapping back around in a circle. So this is going to automatically get us to any number within the range of 0 to 1. So in our example of 10, mod 100 mod 10 is going to be 0. 101 mod 10 is going to be 1, 2, 3, 4, 5. And obviously that's going to have what's called a collision. So let's do the example there. So in our example A here, okay, so, and let's grab our example hash function here. Man, my like mouse is not working on my floor here. Anyways, so suppose, oopsie. Just a smidge bigger. So suppose, yeah. So we have our hash function working normally, and you know what, I want to split this out into its own text box because it's getting difficult. And then how do I select these arrows, man? Oh, it's part of the text box. Awesome. Oh boy, I love Excalidraw. I want to grab the I want to grab the arrows. God, whatever. Oh. Delete. Sorry about that. And oh my god, I've been on the wrong scene this whole time. Kill me. Kill myself. Oh my god. Oh my god. I'm awful at this, man. I need to get better. Okay. Okay, so yeah. There is our, what's it called? There's our indices. Here's how we're trying to index in, right? 0 mod 10 maps to 0. 1 mod 10 maps to 1. 2 mod 10 maps to 2. 3 mod 10 maps to 3. Okay. What happens when we do function 100? It's going to map to 0. All right. This is what we call a hash table collision. Collisions are what we do not want, right? In fact, let me go through and, God, I don't want to re-explain any of that, man. Oh my God, I was gonna try and make a fucking clip out of this section. I messed up, and I can't make the clip out of it. Now I'm pissed. Oh well. Okay, I just gotta move on. So, all right, we wanted to design a hash function that minimizes collisions. Simple hash functions. Creating a simple hash function. Yep. Here's a simple but effective hash function by Daniel J. Bernstein. Okay. Cool. So we're hashing a string. We multiply the hash, some value by whatever, and just add to it. Okay. So this hash function is like a seed. Okay, yeah. So you know what? The way this hash function works is we start off with a seed, multiply it by some value, and add in our like our key. Add in like the value of the character, but that's for a your Wikipedia on hash functions. Yeah, give me some hash values, some hash functions. So Loki, the modulo. Modulo is a good hash function. That's fine. Efficiency, universality, applicability, deterministic. Yeah, okay. Give me some example hash functions. Multiplicative hashing. Standard multiplicative hashing uses this formula, which produces a hash value 0 through m minus 1. Value a is an approximately chosen value that should be relatively prime to w. It should be large. And it's binary representation, a random mix of ones and zeros. Interesting. Fibonacci hashing, Zobrist hashing. Yeah, history. Hash function by Harvey Mudd College. Okay, so simple hash functions here. This is a good simple hash function. Division method, Corman. Choose a prime number that isn't close to a power of 2. Hash of the value k is k mod m. Works badly for many types of patterns and input. H of k plus 3 mod m. Okay, choose m to be a power of 2. Let a be some random looking real number. Donald Knuth suggests m times 0.5 times square root 5 minus 1, then do the following. K times a, x is the fractional part of s, h of k equals floor m times x. Okay, so s is equal to the floor of a times 2 to the power of w. Okay, yeah, so this is going to be our hash function, all right? So let's copy this over and take a look at it. All right, so this is going to be our hash function. Okay, we only have 30 minutes to implement this. I think I can speed through this. Okay, so, and we want to define a to be what? A Knuth suggests random looking real number. Sure. Yeah, that'll work. And we'll say A equals this. And what is P in this hash function? Extract the P most significant bits. To this quickly, let integer let W be the number of bits in the word, and suppose M is 2 to the power of P. What is M? Man. Choose M to be a power of 2. Floor of M times X. Okay, M is the size of the hash table. Okay, thank you. So 2 to the power of what? I think 8 is our hash table. So the P most significant bits from X, K times S. Okay. I think I can understand this. Man. Okay, so let's break down this hash function, I think. So here, go away. Multiplication method. Corman. So choose M to be a power of 2. Okay, so that's the size of the hash table. So in basic, the biggest array we can have is 255. So here, let's annotate this a bit. So M equals is a power of 2, 256. Okay, this is the size of the hash table. Size of hash table. And let's like make our comment in like gray or whatever. Like, yeah. Oh, I can't do it. The whole thing, it turns gray. That's awesome. Whatever. Okay, so that's the size of the hash table. We can add a comment in line. Okay, and then A is going to be some random number, and here we can close that. Let A be some random looking real number. Knuth suggests this random number. So it's a random looking real number. Okay, let W be, what is W? It's the number of bits in a word. Okay, so it's 8. So we're allowed 8 bits in a word. So S is going to end up being a constant value. Okay, so we can low-key get rid of A here and pre-calculate this. So I'm trying to work out the formula here. So S is going to be a constant value now. Okay, so, and then K times S. Hash function of K is going to be K times S, right shifted 8 minus P, where i.e. right shift X by W minus P bits, i.e. extract the P most significant bits from X. Okay, now what is P? Patterns in the data. K, HK is a size buckets. Just a prime that isn't close to the number of the power of K. H of K equals K mod M. This is not a clear website. Well, where am I? HMC? Harvey Mudd College, I think. Harvey Mudd, this is not clear. P. Suppose m is 2 to the power of p. So I guess it's 8. So we want the 8 most significant bits. How big is an int? Or how big is a real number in BASIC? How big is a float in Commodore 64 BASIC? And I'm probably fudging up all of this. Takes up 5 bytes of memory when stored in RAM. 40 bits. How to extract a byte from a float in BASIC. In Commodore 64. Okay, floating point arithmetic. So byte 0. So I can just turn this into a peak. I wonder, can I use a peak? Commodore 64 BASIC peak. Or no, we want def, because we're trying to define a function. And then what's it called? Okay, peak is valid. Boom. Okay. Okay. So how to find a variable's memory address in BASIC. So we're just going to extract like the memory location of a variable. So I should be able to peek a spot on here. Free BASIC RAM. Indexed variables, normal variables. Okay, I think this is where we can look. All right. Stir end, free top, mem size. Okay. Memory location of variables. I believe that hack jam has what you need. Please come for the link. A call to B08B seems to check if a new variable declaration is a duplicate of an existing variable. If it is, it returns the address of the variable in 47 through 48. So this does something. Save current variable to high byte. Basic ROM page. Oh gosh, I'm in over my head. Can you cast a float to an int? Can you cast float to an int in Commodore 64 BASIC? Floating point arithmetic. Okay. Representation. Conversion. Okay. Beautiful. As a C language expression. Okay. Expansion. As a C language like expression. Okay. I want to get, we're trying to get is the most significant byte of the float here. Absolute value int to the smallest integer. Okay, that's promising. How big is an int in Commodore BASIC? I wonder. To round numbers. Rack. Fix implementation. Man, you know what? It might just be expedient to to int and mod it. The absolute value of the float. Turn the value into the smallest integer. Yeah, it might be worth it to abs int. So okay. So here's our goal. We want to take x, multiply the key times s, and then I think what we want to do is do, and I think this is going to be a positive value. So it'll be, or no, we don't necessarily know. So it'll be absolute value of x converted to an int, and then Commodore 64 mod. Nope, not models. Mod. Nope. Okay. Keywords. I know it'll be on the wiki somewhere. Basic keywords. Basic command. Oh lordy. Def. Provide some functions. Function absolute value and something. Ask cosine exponent. Function FRE. Those are all possible. Okay. Basic modulo. Commodore 64. Oh my gosh, I don't know if basic has the modulo operator. You're kidding. Do I have to implement the basic do I have to implement modulo? Well, okay. All right. I guess that'll do. It's so funny. Okay. All right. Well. Okay, yeah, so we can just AND with 255. So I guess that'll get the least significant bits, but whatever, man. I don't care anymore. Abs x or AND x with 255. So that's how we want our hash function to work. Okay. So all right, let's get back to writing our program. Oh boy. Okay. So we'll want to start off with some constant. So we'll have s is going to be equal to, and I need this tab open for a second. I think you guys can see that, especially if I move it over here. So s is going to be equal to what is that? Floor is basic have floor. Is that a thing? No. Okay, well, it has square root. So instead of floor, we can say int. And you know, this is probably going to be a very shoddy hash table by the time I'm done mutilating it. But int 0.5 times the square root, and do we have a square root function? Let's look. SQR, mathematical function for the square root of a number. Okay, we do have squirt. SQR 5 minus 1 times 256, close paren, enter, print, and then let's just do a quick line 20 print s run 158 print s. Okay, you know what, man? Sure, why not? Why the hell not is what I say. List. Oops, not lit. List. Okay, so there we go. So then on line, let's say line 15, we want to define our hash function. Def hash. Is hash already a thing? Okay, hash. Syntax error. Hash 1. Syntax error. Okay, it doesn't seem to be a thing. List. On line 15, we want to define a function. We can say, oh, go back here. So we'll def a function hash that takes in a value x and is equal to and we have all these numeric functions that we get to work with, but I think I've already broken it down to this. The integer of we want to and x, or we want to and the absolute value of x and 255 1 2, and we're missing something here. Int open 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 close close close, and yeah, we have to multiply x times s, or really k times s, and we end that with 255 close parentheses, close parentheses. Okay, and you see I changed the order of, what's it called? I changed the order of our like function, of the functions there. I swapped the and the absolute value because I didn't want to mess up maybe the logical and. So I think we can just call this now. So I want to say like function hash of 1. Syntax error. Okay. So how do I invoke a function? Oh, Commodore 64 basic. Def. Okay, maybe I have to use it. So let's say 20 print function hash of 1. And then run the program. Syntax error on line 20. Okay. So let's just, I don't know. It says I can do this. 20 print fn hash of, yeah, like 1 or like 10. Run. Syntax error in line 20. What is the syntax error? Can't tell. Oh, does the function itself have a syntax error? Def. Here, you know what? Let's line on line 18, like def function ftest x equals x times 3. Function ftest of 3. Go to 18. Go to 18. List undeft function. Okay. It defines a function with exactly one singular numeric argument, consisting of mathematical and logical operands. Okay. Undeft function. Error in 20. Oh. Go to 15. Syntax error in 20. Okay, let's build up the hash function slowly. And I guess I'll have to chop up clip. This was a good practice. I think the next stream I do, I'll make sure, and I'll grind, and I'll make sure I can get that clip, the whole video cut of making a hash table. I'll re-explain everything. It's going to be great. Yep. Um, let's do 20 print fn ftest 3 run. Okay, it prints 9. Okay, so that means we know how to def a function. But let's keep going. So let's clear line 18, clear line 20. Okay, let's change line 15 to def fn hash value of k, and it's going to be equal to int, or no, okay, so let's go inside out. Absolute value of k times s. How about that? And 20 print hash of, I don't know, 39. Oh gosh. 20 print hash 39 run. Bad subscript error 20 list. Def function hash k equals absolute value of k times s. Can I not include outside values? That's a question. The def function 15 def function hash taking the value of k equals absolute value of k. Run. Add subscript error in 20 list. Man, I don't know. Oh, 20 print function hash 39 run. 39. Okay. 15 def function hash k equals the absolute value of k times s. Run. 6162. Okay, beautiful. All right, let's keep adding. Let's add another layer. Okay, so 15 should be def function hash k, which equals and abs k times s with 255. Run. So next error in 20. Okay, so I remember I saw this on the website here, on the wiki, and does not appear to be a function. Basic keyword and, see and basic. So yeah, so actually it'll be 15 def function hash k, and it should be equal the parentheses absolute value of k times s and 255. 20, and then run. So it becomes the value 18. So, and just real quick, 256, and 255. Print 256 and 255. 0. Okay, that's what I expected. Beautiful. So let's keep going. Line 15, def function hash function k equals the we'll just convert it to an int. Absolute value of k times s and 255. And I think that's it. I think that's our hash function, because we list our program. So we define our s to be this nice random value. Then we define our hash function. Then we test our hash function. Low-key, so 256 and 255 actually defines the line 256. Undo that. Run. So hash at 39, 20, and you know what? 20 for I to I equal, oh my goodness, equals, let's say 50, I equals 0, or no, let's say it's negative 10, negative 50 to 50, print function hash, or no, print question mark function hash I next, run. Okay, and it looks like we have what are some nice values. 230, 132, 34, 192, 94, 252, 154, 56. It looks like these are all even numbers. Wait a minute. Our hash function is bad. Okay, so a hash function, the goal of a hash function is to be like well randomly distributed among, you know, the comment, among the size of the array. So here, wait, list. Print function hash at I next. And wait, maybe you want to remove, oops, remove the spacing, run. Yes, okay. So yeah, so interesting. I've managed to make a hash function where all of the hash table results are odd, are even rather. I don't know why they're all even. That is so weird. Okay, S. Okay, so because I'm guessing 11 print S run. Yes, because S is an even number. Okay, list. Let's clear line 11. 10S equals, goodness, equals int 0.5 times the square root 5 minus 1, not times in, or I guess let's do it times 255 instead. 11 print S, run. Okay, so next we're in 10S. 10S equals int 0.5 times the square root, times the square root of 5 minus 1. Oh, I accidentally added another, what's it called? Parenthesis I didn't need. Run. Okay, that's odd. It's 0.5 times the square root of 5 minus 1 times 255. Wait, what was the hash function? Oh, you should be in, that's why I added the extra one. Okay, S equals, okay, so what's happened here? Okay, so at first I made a hash function where, all right, so remember any number multiplied by an even number becomes an even number. That's bad. We don't want that in hash table. So our hash value has to be odd, actually. Or no, our hash like seed value, our S has to be odd. So what we really want is S to be equal, gosh, I'm a fool, to an integer, which is 0.5 times the square root of 5 minus 1 at times 255. Now we can, the hash value is now 30. Man, what is wrong with this? Why is it not working? List. Okay. 0.5 times the square root of 5. Oh, is it because of precedence? So I need to insert some parentheses here. Now run. Okay, that looks way better. Okay, there are still some collisions, and in fact, you'll see that the negative numbers are actually the inverse of the positive numbers. This will be more clear if I do here. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, if it, I change it to this, so 20 for I equals negative 4 to 4 print function hash I next run. Okay, so you'll see that the negative numbers are in fact just the inverse of the positive numbers. So I'm wondering, that's because we do our absolute value. So I bet if we change something right here, I bet if we get rid of this absolute value right here, we should be golden because of how negative numbers work under the hood. Perfect. Okay. The stream is over. What we've done is we've created a hash function. Next stream, I'm going to take this hash function and I'm going to build out a hash table with it. It's going to be great. Don't miss it. We're going to do Leetcodes with our hash table that we build next stream. I might even figure out how to save stuff to the basic drive so we can use it later. But yeah, so this has been my stream. Hope you enjoyed it. Thank you for watching. If you did, oh my, yeah, no, okay, wait, you were able to see it. I was the only one on that stream. Okay. Yeah, thanks for watching. This has been Code Orangutan, and I will see you later.